Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. We thank you for the weekend about to start, and just pray that you'd help us to glorify you what we do this day, Lord. In your name I pray. Amen. All right, where are we? So, theorem. This is sometimes called the plus-minus theorem, at least in Howard Anton's linear algebra book. And what's this theorem say? It says that if S is linearly independent subset of vector space V over field F, and if we pick X, which is not an element of the span of S, all right, then what do we get to say? S union, this vector S union X is what? Fill in the blank. What's that? Linearly independent, right. So if we take something outside the span, then by definition there's no linear dependence of the vectors generating the span, right, which attains X, which is to say that S put together with X is linearly independent, right? And then that's the plus of the plus-minus theorem. What's the minus? It says that if the minus, I always forget the statement of the minus. Second here, I'll get on the straight and narrow here in a second. V in S is linear combination of other vectors in S, if and only if what? If and only if the span of S is the same as the span of S with V removed. So by the way, guys, just so we're clear, I know there's two popular notations for set difference, but for me, when I write something like S minus T, what that means is S and S such that S is not in T. So this is, set difference. Sometimes people use like a backslash or forward slash or something, I forget. But anyway, that's the other thing. If removing the vector doesn't change the span, that means that that vector is a linear combination of the other vectors in the set. Right? Okay? So theorem, if W is a subspace of V, over F, right? And well, I'm just going to keep it simple here. The dimension of V is equal to n. I'll give you the finite dimensional argument. All right. Then there exists a basis for W and the number of things in the basis for W, right, is less than or equal to n. Thus, what? How can we compare it? We can compare the dimension of the subspace to the dimension of the total space, right? The dimension of V, dimension of W, is less than or equal to the dimension of V. Right? We could say more. how about when is equality reached? Moreover, the dimension of W equals to the dimension of V, right? If and only if what? V is equal to W. All right. These are all things we can prove. All right, let's prove them. So let W be a subspace of a vector space V of finite dimension, all right? Okay? Of course, I'm assuming n is a natural number, like it's 1, 2, 3, 4, something like that. Okay? So what's the worst case for W in some sense? Like, what's the smallest it could be? So we can have W equal to 0, right? If W equals to 0, well, then that's the span of what? The empty set by our definition over the field, right? And the number of things in the empty set is what? 0, right? So the dimension of the 0 space is equal to 0, which of course is what? Less than n. So I think we're okay with the 0 space, right? No trouble there. So what else then? What's the other possibility? Either W is 0 or what? Alternatively, what do we have? W is not equal to 0, right? And W is, of course, a subset of V, right? Could be equal to in this case, right? Doesn't have to be a proper subset. Could be the whole set. But if it's non-zero, what does this mean? There exists x1 in W, right? x1 not equal to 0, right? So, you know, if the span of x1 is equal to W, then what? Then the set containing x1 is a basis for W. W is a one-dimensional subspace, and we're done, right? Because 1 is less than or equal to. And let's see here. I don't have the less than or equal to n. Maybe I need to. Well, anyway, we'll get back to that. But anyway, this much is true. That proves. Let's forget about the less than or equal to n for a moment. Let's just focus on the fact that this gives us a basis for W, right? Hence, beta equal to x1 is basis for W, right? Else, the span of x1 is not equal to W, right? So what's that mean? There exists a W2, an x2, right? In W with x2 not in the span, right, of x1. So by the plus of the plus minus theorem, that allows me to construct, if I look at beta, let me call it beta sub 2, with x1 and x2 in it, is linearly independent, right? So I joined a vector. It's linearly independent. Yep.
You said x2 was not in the span of x1?
I did say that. I did say that. What I didn't do was to write it. Thank you. Kind of an important little mark on the board, yeah? Thank you. Much appreciated. Now, then what? Maybe you know what's the next thing I'm going to say. If the span of beta 2, what? If the span of beta 2 is equal to W, then beta 2 is basis for W, right? Otherwise, what? There exists an x3 outside the span, and we can adjoin it to beta 2 to get a set with 3 vectors, which is linearly independent, right? We can continue in this fashion, right? And this has to terminate. Why? It can't go on forever and ever. It's not an endless, loop. Right, because n is finite. The largest number of vectors we can have in this set, which are linearly independent, is the dimension, right? So, continuing in this fashion, we have constructed a basis, right? Say beta sub W for W. Now, why? Now, there's one thing. I've claimed more than that in this theorem, right? So at the moment, we've just kind of sketched a lot of the proof of why there exists a basis for W, right? So my question is, why is the number of vectors in the basis for W have to be less than or equal to n? This is a pretty easy proof by contradiction. Suppose that the number of vectors in the basis for W was greater than n, right? What would that imply? That would imply that you have the span of beta sub W, right? Well, that's a subset of V, right? We could use the same argument to extend beta sub W to a basis for all of V, right? So extend beta sub W to beta sub tilde, a basis for V. Right? How many vectors are in, what's the number of beta tilde? Well, it's greater than the number of what? Beta W, right? Which is greater than what? N. Oh no, we just constructed a basis for the whole vector space, which has more than n vectors. This is very embarrassing because we spent like a long time last time proving that if there's a basis with a finite number of vectors, then any other basis for the vector space must also have that same finite number of vectors, right? So that's a contradiction, which means what? What's the wrong thing? This is the source of this poison, right? So apparently, the number of vectors in the basis for a subspace is less than or equal to n. And essentially the same line of logic gives you equality when the dimension matches, right? Because if the dimension of the subspace is matching the dimension of the whole space, that means that there's a spanning set, right, for the subspace which has n vectors. But a spanning set with n vectors must span the whole space by the dimension theorem we proved last time. All right? So there's that. The other thing which is important for you guys to know about, and also important for you to be able to use, let's say conscientiously, like carefully, all right, and not when you're not supposed to. And this is the tough part, is because when I ask you to prove these various theorems on the test, you inevitably will give me a logically equivalent theorem and say I'm done. It's really hard for me to get you guys to prove what I want you to prove when I ask about these things. But I'm working on that. I'll figure out a way to pin you in a corner, make you prove what I want you to prove. I'll figure it out. Or maybe I won't have time and you'll get out of it. I don't know. We'll see. So if V is n-dimensional over F, and S has n vectors, all right? S is a subset of V, okay? Not a subspace, but a subset. The following are equivalent. 1, S is a basis for V. 2, S is linearly independent. 3, V is equal to the span of S. The proof of this is very, very much similar to what we've already done today. It basically just rests on the plus-minus theorem. I'll just prove one of these things, okay? So let's pick on let's pick on 2 implies 3, okay? So assume 2 is true. So assume S is linearly independent, and the number of things in S is equal to n, where n is also equal to the dimension of the vector space V, right? What do we want to prove? Yeah, we want to prove that S is a spanning set. It's a generating set for V. How should I do that? Well, certainly span S, right, is what? Remember? Span S is a subspace of V, right? What's the dimension of span S? Can you tell me what the dimension of span S with what we've got here?
Someone just said n.
Oh, someone said n? What's wrong with my hearing? Was that you? It would be funny if it was you, the first person who said it.
I was thinking it, but that's no proof.
Oh.
There's the knowledge crowd.
Yeah, I'm sorry. Like it must. This is always a danger as an instructor. Like you think nobody said anything. All you have heard the person say "n." You're like, why are you staring at us? You know, like what's going on? So, yeah, check it out. We've got a subspace of dimension n. So by our previous theorem for today, it's everything. Right? And so if you don't trust that, I didn't really go through the details of that part of the theorem we're using here, right? So let's see here. Suppose, just to make sure we all understand, suppose it were not true. I think that actually, I mean, if you accept that I've completed the proof of the previous theorem, we're done, because we've shown that the subspace has the same dimension as the total space, which means that the subspace is the whole space, which is what we're trying to prove for 3. Suppose you don't believe me. Suppose you mistrust my proof of the previous theorem, which was incomplete, right? How would we actually supply detailed arguments here? How about this? Suppose span S is not equal to V, right? Then what? Then there exists X in V with x not in the span of S. And what's that say? That says that S union that extra vector x is linearly independent. Subset of what? Subset of V. This is very troubling because we just found, yep. Did it again? Dang it. I did it again.
They didn't wait till the end of class to point it out.
That is true. So that reminds me, I had a sum over k, which is not okay. It was supposed to be the sum over I believe. I equals 1 to k, and like I was... Anyway. So that's a linearly independent subset of V. Well, this is most troubling because that means we have a subset of V with n plus 1 vectors, which is a span, maybe that's not a spanning set, but we could do what? We keep appending vectors to it till we get to a spanning set, right? And then we'd have a linearly independent spanning set for the whole vector space, which is got more than n vectors, which is very troubling since the dimension is n. So, anyway, I hope I've showed you enough that given time and a clear starting point, you could prove these things for yourself, right? Well, that's new. Some train aficionado in here. It's I kind of like that. I don't know. All right. So guys, just a few comments. I won't really say much more about this, but there are a few other things we can do with subspaces. Like, how do you build new subspaces from old? I'm just going to rattle off a few things we can do. I'm not going to say much more about them here. These are things we come back to from time to time. But other vector space constructions, let's say. So, number one, if we have V1 and V2 vector spaces over a field F, then you can make the Cartesian product of V1 and V2 a vector space over F. And the way you do that is very simple. So how do you define? It's very simple. So we do like x1, y1. I'm sorry, x1, x2 plus y1, y2. Those are two typical elements of the Cartesian product of V1 and V2. How are we going to define the sum? And how about the scalar multiple? Goodness gracious. So can you help me out? I'll do the easy one. This one would be c times x1, c times x2. And you can sort it out. That will satisfy all the necessary axioms to be a vector space as it filters through the scalar multiplication. But of course, we have to. How do you add pairs of vectors? Yeah, component-wise, right? So that thing we did. Basically, to make R2 from R, well, it also works. If you want to, I mean, and V1 and V2 can be radically different things. I mean, we could be looking at something really silly. Like an example of this would be something like, I don't know, you could let your vector space be 2 by 2 real matrices, Cartesian product with, like, I don't know, polynomials. I mean, that's a legitimate vector space. I mean, weird, but typical elements of it are pairs of 2 by 2 real matrices and polynomials. It's an infinite dimensional vector space. You want me to make it finite dimensional? Here. There. Now it's pairs of 2 by 2 matrices and cubic polynomials. So a typical element in this vector space would look like A, B, C, D, comma, this guy, A, oops, need new letters, A1 plus A2x plus A3x squared plus A4x cubed. There you go. That's a typical element in this Cartesian product of vector spaces. I wonder, can you guys tell me its dimension? What's the dimension of this V? Anyone guess? 3. 8. We have winner. Yes, 8. Yeah, because it's just the number of independent parameters. 1, 2, 3, 4, 5, 6, 7, 8. You can pull those out and write this. Here's the first one. A 1, 0, 0, 0, 0. Da da da. Plus eventually you get to A4 times the 0 matrix x cubed. And there's 6 things in between there I didn't write. You can prove that those are linearly independent, in fact. So if we trust Taylor's intuition, then what's the dimension of V cross W, V1 cross V2? For other thing, I mean, what would be the dimension? What do you guys think? What's the dimension of V1 cross? Since we're so, what do you think that should be? Indeed, it is in fact just the sum of the dimensions. How would you construct a basis? Here's what you do. The basis for this guy you can form by taking essentially the basis for the first vector space crossed with the 0 vector and unioning that with the 0 vector. So this is the 0 vector for the second space. This is the 0 vector for the first space, Cartesian product with beta 2. So that concatenation will serve as a basis for this Cartesian product. You just append zeros and make them into tuples. None of this is really terribly surprising if you start thinking about what is Rn. What's R5? R5 you could think of as R2 cross R3. Right? So like 2 plus 3 is 5. And you could, anyway. Not the greatest example, but there are other things. Subspaces. Subspace fun. What fun can we have with subspaces? Well, if we have U and W are subspaces of V over F, then there are several popular subspaces to think about. One you could think about is the intersection, the set theoretic intersection of U and W. This is also a subspace of V. This is a homework problem you have. Prove that the intersection of two subspaces is a subspace. You already turned the homework in, right? So what's the proof? Zeros in both. If you take x and y in the intersection, then the sum is in each because they're each a subspace. The scalar multiple of x is in each because they're each a subspace, which proves that cx plus y is in both. Consequently, cx plus y is in the intersection, which shows that the intersection passes the subspace test. Was this hard? I hope not. I always tell you guys, because it's important piece of my personal history of teaching this course. There was a semester I gave no one an A. Not a person. And you know why? Because no one on my final could solve that question. And to me, if a whole class in linear algebra cannot prove that the intersection of subspaces is a subspace, some of you are lost on it right now. That is understandable. But 2 months from now, after I've posted solutions, and it's been on the next test, and then it appears again on the final, and you still can't do it, I can't give A's. I mean, it's just how it is. That's not you guys. There's there's going to be A's in here, I'm pretty sure. But, I mean, I hate it. I hate it. I of course, I want to give A's, but I just couldn't. I was honor bound by previous classes to not do it. So sad. Anyway, also this, we can define, so this is defined by set theory, right? I don't need to do anything more for that, but this we have to give a definition for. U plus W, what's that? What this is like x plus y such that x is in U and y is in W. The sum. This is called the sum of U and W. That is also, you can prove, again, it's very boring. How is the subspace test? You can prove by the subspace test that's a subspace of V. All right. And what's the story here? What's the relation between these guys? We have the following. We have that the intersection, right, is a subspace, in fact, of the sum, right? Well, I could say this. This is a subspace. I can put U here, right? And U is a subspace of the sum. Do you see that? Do you see why U has to be a subspace of U plus W? Just look at the set. Put y equal to 0 in the definition. You get everything in U. I could just as well have put W here. That would also be true. I just don't want to put it in this string because I don't know which one comes first. Okay? And then this, of course, is a subspace of V. If you want me to put something below it, 0, right? So let's see here. U intersect V is what? It's the largest subspace contained what? In both U and V. What's U plus W? It's the smallest subspace which contains both U and W. Contained in versus containing both. Those are different things. How are these related? Well, there is a theorem. Here's how it goes. The dimension of U plus W, all right, it's equal to the dimension of U plus the dimension of W minus the dimension of the intersection. That's how they're related. Yep.
Isn't U intersected with V the same thing as U?
U intersect V. Oh, that's a, yes. I was not done writing there yet. I'm glad you pointed that out. Thank you. Yeah. Sadness. I think that's worse than the not writing not element of. It's worse than the not nodding. Hey, if I not nodded, doesn't that mean I didn't make a mistake? Because isn't not nodding like not a not? Someone say please don't. I respect that. You can draw a picture of this, which is a lie. So if we look at U, right? If we look at V, right? Excuse me, look at W, right? Then if you add all these together, the whole space is U plus W, right? V's bigger still, but anyway, this is what? U intersect W. So you can kind of see this formula making sense. You take the dimension of this, the number of things in here, plus the number of things in there. You subtract the number of things in there. So that gives you the, see, it doesn't quite work. I mean, dimension is not number of things, is it? So I really should erase this. This is just bad. It's at best a fuzzy analogy to the counting formula for, what is this? Is it conditional probabilities or, yeah. It's a fuzzy analogy. Okay. So that's vector spaces. I guess we're done. So the last section in chapter 6 is on reinterpreting solution sets as what are called linear manifolds. I'm just going to skip over that for now. We'll come back to it as we need it. If it's in the homework, great. But our next topic, this is a big one, is linear transformations. All right, so let's get started on that. So this is, of course, the next chapter. I really think that linear transformations help draw together the last chapter, make it even more meaningful. Vector spaces without linear transformations, they're kind of hollow. It's just an incomplete discussion. There are other terms for a linear transformation. So other equivalent terms, linear operator, a linear operator, or a linear map. Sometimes I use these three terms pretty much interchangeably. Okay, so what is a linear transformation? What's a linear operator? Is usually used when the domain and the range are function spaces. So like the differentiation operator is a linear operator because differentiation takes in a function and spits out a function, right? So like differentiation is a linear operator. But you could say it's a linear transformation on function space. That wouldn't be wrong. Okay, so definition. If we have t, which is a function from v to w, v and w vector spaces over some field f, then t is linear transformation and we write t is an element of LVW. So like the set of all linear transformations is script LVW. There are other notations for this. Sometimes people will call this hom sub f VW, another popular notation for this thing. Anyway, provided what? Two things. Number one, t of x plus y is t of x plus t of y for all x and y in V. And two, t of c times x is equal to c times t of x for all x in V and c in F. So number one is known as additivity, right? Number two, a lot of books call homogeneity. My brother doesn't like that because homogeneous functions mean something more general. Technically, it's a homogeneous function of degree 1. Homogeneous degree k would mean that you can pull c out with the power k. Like f of x equals x squared is homogeneous with the degree 2 because if you look at f of cx, you get cx squared. You could pull c squared out. But I will just say homogeneous to mean homogeneous degree 1, and you guys won't get confused because we're not really discussing the more general problem of homogeneity in here. Okay. Any questions? All right. So are there any examples you can think of? There are two kind of stupid examples that you can always give. How about the zero map? What if you just take everything in the vector space V and map it to the zero vector in W? Is that a linear transformation? T of x equals to 0 sub W for all x in V, right? It's easy to check that that's additive and homogeneous linear transformation. Yay. Another example, how about this? Oh, see, I need more. If V equals to W, then we can define T of x equals to what? It makes sense to write, if V and W are equal, right? What can I do? I could just put x again, right? Would this be a linear transformation? If you look at T of x plus y, that would give you x plus y, which would be T of x plus T of y. It's additive. Can you pull a scalar out? It's easy to check 1 and 2 hold for this. This, of course, is called the what? T is called the identity map on V, right? And by the way, in this case, the linear transformations from V to V, sometimes use the notation just L of V. These are also known as end V. This is for endomorphisms. An endomorphism is simply a linear transformation. An endomorphism is simply a linear transformation from a vector space to itself. Okay, so the identity map on a vector space is an endomorphism. In fact, it's invertible too, right? Like, what's the inverse of the identity map? How can I undo the identity map? Just do it again, right? So if you go back to think about your basic set theory and inverse functions, the inverse function of the identity map, of course, is the identity map. What's the inverse of the zero map? Or, I mean, does it even make sense? Can I find a map which goes in the reverse direction there? I don't think so, no. Okay, so moving on. Unless there's a question. So I got a bunch of nice examples there for you to read. I'm going to go on and prove the next fundamental thing. Theorem. Again, assume T is as in the definition, okay? Then T of the sum, I equals 1 to n of Ci Vi is equal to the sum I equals 1 to n of Ci T of Vi. In other words, I'm saying the definition extends. If you have it for 2 things, you have it for n things, right? The linear transformation of a linear combination is the linear combination of the images. Images, what do I mean images? This is the image of V sub I under T. Our next theorem is that, again, T as in the definition, okay? T of 0 is equal to 0. How would we prove this? How about this? T of 0 plus 0 is equal to T of 0 plus T of 0 by additivity, right? But of course, this is what? T of 0, right? By the cancellation lemma, I mean, I can put it up here. This together implies that T of 0 equals to 0, right? By cancellation lemma. So it's a straightforward consequence of additivity. I don't think I even need homogeneity there, actually. Another theorem. If I have time. Debatable. Ah, yes. If S is a subset of V, if this is linearly dependent, all right, then T of S, which is a subset of W, is also linearly dependent. So if you have the image of a linearly independent, the image of a linearly dependent set is once more linearly dependent. How's this proved? Well, so you've got the sum, right, of CI/SI equals to 0, where all the CI's are not necessarily, I mean, for some CI being non-zero, right, it's a linear dependence of vectors in S. And what happens when you feed T to that? What happens here? Well, because of the previous theorem, we can pull the sum out. Right? So there you go. That is a linear dependence of T of S. What does T of S mean, guys? What's this mean? This is set theoretic notation, right? That's a set. This is the set of images. This is T of SI such that SI is in S. It's the image of S under T. That is a linearly dependent set because I've just shown you that if we have a linear dependence in S, we feed it to the linear transformation, it passes through to the same linear dependence of the images. Now, this doesn't have to be an interesting linear dependence in W, right? This argument works for the 0 map over there. It may not be that interesting, right? The image, T of S could be just 0, you know? So how about this then? Next question. We'll stop for today. But what if S was linearly independent? Right? Would the image of a linearly independent set under a linear transformation be linearly independent? We already have one clear vote against this. The 0 map. It sends everything to 0. The set containing 0 is linearly dependent, right? So certainly my claim cannot be true in general. What data do we need? What structure do we need for a linear transformation to maintain, to preserve linear independence from its domain to its codomain? Right? That's one of the big questions that looms over us going forward. So anyway, this is what we're doing. We study linear transformations. We'll say how to find their matrix, their properties, what insight they give us about vector spaces. By the way, you've already been working with them. The coordinate map is a linear transformation. That's what the lemma proved. The lemma proved that the coordinate map was a linear transformation from the vector space to the field over which it's built, and tuples. Anyway, I shut up. Have a good weekend, you guys.